Hello, everyone. Thank you for joining us for today's EEA Education Series Interest Group. Today, we will be discussing an introduction to Layer 2 solutions for Ethereum scaling in ATech Encore. Everyone is in listen-only mode. However, you're encouraged to ask questions by using the questions box on your control panel. Today's call is being recorded and will be available to all attendees soon after today's presentation. The Enterprise Ethereum Alliance is a member-driven standards organization whose charter is to develop open blockchain specifications that drive harmonization and interoperability for businesses and consumers worldwide. We welcome any and everyone to join and become a part of our global community. At this time, we are pleased to introduce today's speaker, Tas Dienes.
All right, thanks, Teresa. So let me share my screen. Here we go. All right, so yeah, today we have a talk about Layer 2 scaling solutions for Ethereum. I'm Tas Dienes. I work at the Ethereum Foundation on ecosystem support, which includes a lot of things, but one of the things I do is chair the Mainnet working group at the EEA. And so today we'll have a two-part webinar. The first hour is kind of a high-level overview of what Layer 2 is, why we need it, how it fits into the Ethereum landscape, and a really, really brief overview of the various Layer 2 technologies, and then some things to think about when choosing a Layer 2 solution. Then we'll have a 15 or 20-minute panel discussion with representatives from 3 of the important Layer 2 projects in the Ethereum ecosystem. And in the second hour, we'll get a little bit more technical, and we'll have an overview of Optimism, optimistic rollups, Arbitrum, sidechains and state channels, and Matter Labs, ZK Sync, and ZK Porter by representatives from each of those projects, followed by a slightly more technical panel discussion of those of Layer 2 with those representatives. So what's the problem Layer 2 is trying to solve? The scaling challenge that we have is that Ethereum mainnet today can process on the order of 30 transactions per second, give or take. This has increased a bit over the last few years as block size limits or block gas limits have increased. But this can only go so far. So we might be able to squeeze 10x or with some clever optimization, maybe 100x more out of Layer 1, but not 100,000 times or a million times more, which is what we really want to do some of the really more interesting applications. And this is true for most public blockchains in general. So if a public blockchain says otherwise, if they claim that they can do thousands of transactions per second, they're probably sacrificing either decentralization or security. And this is because of this thing called the scalability trilemma, which says that you can have 2 of the 3 scale, security, and decentralization, but you can't have all 3 on a single shard at least. So generally, the quote scalable public blockchains are sacrificing either decentralization or security in order to achieve that. But we want more capacity because we want to be able to do things that require high throughput, hundreds of thousands of transactions per second maybe, and we don't want to sacrifice on security or decentralization. So how do we do that? Layer 2 is part of the solution at least. And what Layer 2 is a set of protocols that run on top of Ethereum, which is Layer 1. And the protocols inherit security properties from Layer 1 and provide greater transaction processing capacity or throughput than Layer 1 can provide. So Layer 2 scaling solutions are secured by Layer 1, so they have that security, but they enable blockchain applications to handle many more users or actions or data than Layer 1 could accommodate by itself. And in this kind of a stack diagram, we have Layer 1 at the bottom, which could be Ethereum 1 or Ethereum 2. And then we can have multiple Layer 2 instances running on top of that. You can have public Layer 2 instances, which are shared by multiple applications. And you can have also private Layer 2 instances that are used only by one application or maybe 1 or 2 applications that they're dedicated to. And then you can still have applications running directly on Layer 1 alongside these. So how does Layer 2 fit together with Ethereum 2? They're actually very, very complementary. So Ethereum 2 introduces sharding, which can get us perhaps 50 to 1000x over time more throughput on layer 1. And layer 2 also increases throughput by some similar orders of magnitude. And if you combine the two, then the scalability increases multiply, and we can get tens of thousands, hundreds of thousands, maybe even more throughput by combining ETH2 with layer 2. So they go together very well. So if we look at private versus public chains, a lot of enterprise applications up until now have been developed on private chains, and oftentimes for pretty good reasons. For example, scalability wasn't there on private chains. On public chains. Privacy is a concern, so whatever data you put on public chain is available to anybody, and that's often not desirable for enterprise applications. But there are still some benefits to public chains. They have stronger security and immutability because of the fact that there are thousands of nodes operating them. There's censorship resistance because they're more decentralized. Transparency can be a pro or a con, but if you want transparency, public chains are an excellent way to achieve it. Interoperability with other applications on mainnet is an important one, so you can get the network effects. And the idea here is similar to building an application on the public internet versus on a private network where it's isolated from the rest of the world. Sometimes it's fine to have an isolated application, but in many cases, it's more valuable to have an application that can interact with other things out there on the network. So building on mainnet provides a common frame of reference that avoids the creation of isolated silos. So a lot of these consortium chains that are being developed today, companies might have to join many different consortia and participate in multiple consortium chains. And these things may not interact with each other or may not sort of communicate. So they develop isolated silos of information. And this can be avoided by using a common frame of reference like a public Ethereum mainnet. And then finally, according to a study by Ernst & Young, building an application on a public chain such as Ethereum mainnet can provide lower total cost of ownership because you don't have to build all the infrastructure and operate the nodes yourself. So if you add layer 2 on top of this, there are even more benefits for enterprise applications, and they can negate some of the concerns or some of the reasons that drove people to build on private chains in the past. So obviously with layer 2, you get more throughput. It solves the throughput problem. And importantly, also you get throughput isolation from other applications. So if there's an application like CryptoKitties, for example, that takes up a lot of, that takes off and eats up a lot of capacity on layer 1, the right layer 2 can sort of isolate you from that or insulate you from that so that your application can still keep chugging along even though layer 1 may be relatively congested by something else. You can also get fast transaction confirmations. So some enterprise applications need kind of quick response times, and you can get that with layer 2. You can have the possibility to pay for transactions in fiat money and to have more predictable costs. So many people have complained about the unpredictability of gas price and the high cost of transactions on layer 1. And also for some enterprises, holding Ether in order to pay for gas on layer 1 is difficult because enterprise organizations just aren't used to this concept of holding tokens and cryptocurrency, and their financial departments may not be comfortable with it. But with layer 2, you can have an operator that you pay in fiat money or whatever other form of payment they're willing to accept, and they can offer you a predictable cost for your transactions. You can also have data compartmentalization or privacy. So you can have a private layer 2 and keep all of the data in that layer 2 network off of layer 1 and away from the public. So if you want to have private transactions between a consortium or within an enterprise and have sensitive data on that blockchain, you can do that on a layer 2 chain and have a private layer 2 chain that keeps the data off of mainnet and maintains privacy. But you still get the benefit of transactions on layer 2 being sort of umpired and secured by layer 1, which still acts as a common frame of reference and ensures globally consistent state management. So you get a lot of the benefits of public chains, but you can avoid some of the pitfalls that have prevented enterprises from building on them today. And I wrote a paper about this recently. It came out on the Ethereum, the EEA blog. So it's called How Ethereum Layer 2 Scaling Solutions Address Barriers to Enterprises Building on Mainnet. Go to antiethalliance.org and look at the blog there to find that. So now onto layers 2 technologies. There are many categories, many flavors to choose from. So we've got state channels, plasma, optimistic rollups, ZK rollups, Validium, sidechains, and hybrid solutions. A bit of history, layer 2 development kind of started around 2016 or 2017. The Lightning Network paper came out in 2016, and that was a state channels layer 2 for Bitcoin to allow more scalable payments on the Bitcoin network. The first layer 2 for Ethereum specifically was Plasma, and the Plasma paper came out in 2017. Then a year later, we got counterfactual state channels, ZK rollups, optimistic rollups, Validium. So it's been a process of sort of planting seeds, watching them germinate, watching layer 2 sort of grow and flower. And finally, we're starting to see the fruits. So we're seeing projects moving on to layer 2. And I think 2021 will really be the year where layer 2 takes off, and we see a lot of things happening on layer 2. So there are many different layer 2 technologies. How do you kind of put them into a framework to conceptualize them? This is one useful way of thinking about how the technologies relate to each other or fit together. So we have a 2x2 matrix here with ZK rollups, optimistic rollups, Validium, and Plasma, and the axes are data. Transaction data storage and computation. So on one axis, we have whether data is stored on chain on layer 1 or off chain, which would be on layer 2. And then we have the possibility for either zero knowledge validity proofs to verify that the layer 2 transactions were computed correctly and the resulting state is valid. Or we have the possibility of interactive deposit slashing or fraud proofs, which is a crypto economic mechanism to ensure that computation is done correctly and the resulting state is valid. So if we look at on-chain data, that is all transaction data is written to layer 1, and zero knowledge validity proofs, we have ZK rollups. So ZK rollups, we'll get into them with more detail later, but ZK rollups use zero knowledge validity proofs to verify that transactions were computed correctly and the state is valid, and store all data on chain. If we do the same validity proofs, but let's store data off chain, we have Validium. And then in the interactive deposit slashing fraud proof department, where we use crypto economic mechanisms to ensure that the data is valid, we have optimistic rollups with all data on chain, and we have Plasma with data being off chain. And then finally, we have sidechains and state channels over here on the side because they don't really fit into this framework. So onto each of the layer 2 technologies separately. So sidechains, I'll start off with. A sidechain is a separate blockchain that runs in parallel to a main chain and operates independently. So it has its own consensus algorithm, which could be proof of authority, proof of stake, whatever, could be anything. And it's connected to the main chain or layer 1 by a two-way bridge. So one advantage of sidechains is scalability because they can achieve pretty high throughput, maybe tens of thousands of transactions per second per sidechain. And they're pretty well-established technology. They've been around for a while. And they can support general computation. So you can have an EVM-compatible sidechain that will run your Solidity smart contracts without too much modification. On the downside, sidechains are not necessarily very decentralized because typically they're run by a small number of nodes or validators. And they're not secured by layer 1. So technically, a sidechain is not even considered a layer 2 because as we said earlier, layer 2 is secured by layer 1. That's one of its definitional properties. And since sidechains are not secured by layer 1, we may not want to call them a layer 2, but I included them here because they're a scalability solution. And it's important to recognize that a quorum of sidechain validators can commit fraud. So if you have, say, 5 validators running a sidechain and 3 of them decide they want to override some transaction, they can do that. Key projects in the sidechain category are the POA network and Scale. Next, we have state channels. So state channels are two-way channels between two parties, and the transactions between the parties take place entirely off of any blockchain and exclusively between the participants, but they're settled on layer 1. So here, if we look at the diagram, you've got Alice and Bob transacting. They initially open a channel by locking some state or tokens, it could be, if they're transacting value, into this channel. And then once they've opened the channel and deposited something into it, they can transact as many times as they want, could be thousands of times. And they can send funds back and forth. And then when they're done, they close the channel out, settle it on layer 1, and walk away. So you can get really high throughput because it's just a direct point-to-point communication. So you can get thousands of transactions per second per channel. And you can have pretty much unlimited channels. If you have many participants, they can each have their own channels. So you can get kind of almost unlimited combined throughput with state channels. Advantages, aside from throughput, you've got fast withdrawal or settling on layer 1 if both parties participate. You can close the channel out quickly. And high throughput, and then you've got low cost per transaction because of the high throughput. So state channels are good for things like streaming micropayments, where you may want to pay for a service by the second. Like if you're streaming audio or video, you might want to pay per second, or if you're making API calls, you might want to pay per API call. So you might be making thousands of payments over the course of hours or days, and you want the transaction cost for each payment to be very, very small. On the downside, there is some time and cost to set up a channel, so they're not really good for occasional one-off transactions between random users. They're more appropriate for repeated transactions between an established or a given stable pair of users. There's also a need to periodically watch the network. So this is called the liveness requirement, which means that if you want to ensure that your counterparty doesn't steal your funds, you need to be online watching the network at least once every few days. The parameters are configurable, but if you go offline for weeks or months, there's the possibility that you'll lose your funds. So you can either do this yourself, or you can delegate this responsibility to a watchtower. And then also there's capital lockup. So as you see here, when the channel is opened, you have to deposit some funds, and you can't really add to those funds without doing another on-chain transaction. So if you want to lock, say, $1,000 in a channel and you want to be able to spend that money over time, that $1,000 is essentially tied up as long as the channel is open, meaning you can't use it for anything else. So there's a capital cost associated with that. And some key projects in this area are Connext, Raiden, Perun, and the State Channels project. Next, we'll look at Plasma. So a Plasma chain is a separate blockchain that is anchored to the Ethereum layer 1 and utilizes layer 1 to arbitrate disputes. So Plasma, because it keeps data off-chain on a private network, can get pretty high scalability. You can probably get tens of thousands of transactions per second per Plasma chain. And you can run many Plasma chains in parallel. So you can kind of multiply this number and get very high throughput with Plasma chains, many Plasma chains combined. So on the upside, you've got high throughput, meaning low cost per transaction. And unlike state channels, Plasma is good for transactions between arbitrary users. So if you have 1,000 users that are on a Plasma chain or in a Plasma network, anyone can transact with anyone else with no kind of overhead or setup cost per pair like you would with state channels. On the downside, Plasma doesn't support general computation, so you can only do basic token transfers or swaps. You can run an exchange on a Plasma chain and a few other transaction types that can be supported via predicate logic, but you can't do sort of general computation or run smart contracts on a Plasma chain. There's the same need to watch the network, the same liveness requirement that you have with state channels. And there's a reliance on one or more operators to store layer 2 data and to serve it upon request. So because the data in a plasma network or a plasma chain is not stored on layer 1, you have to rely on somebody to store it, which is the layer 2 operators. And so if those operators become malicious or disappear and no longer make the data available or no longer serve the data upon request, then the plasma network essentially becomes frozen and cannot transact anymore. You can still withdraw your funds, but you can't transact in the network. And then finally, there's this thing called withdrawal delay. So if you want to take your money out of a plasma network and withdraw it back to layer 1, you need to wait a few days to allow for challenges. This is because it uses a cryptoeconomic dispute mechanism, and you have to wait for challenges to occur. So there's a configurable, but typically several days or even a couple of weeks delay before you can completely use completely withdraw your funds to layer 1 and use them on layer 1. For fungible assets like Ether or your ERC20 tokens, this can be mitigated by liquidity providers, which can offer a pool to exchange layer 1 for layer 2 tokens. But there's capital costs associated with that. So key projects in this space are the OMG network, Matic network, Gazelle, LeapDAO, and Gluon. Now on to optimistic rollups. So with rollups in general, all transactions are written to layer 1 as call data. So that means that your transactions and your state are saved on Ethereum mainnet. It's kind of used as a data availability layer. So the data is stored on mainnet. And call data is a way of writing the data into the Ethereum network at a lower cost than would be the case if you were doing the transactions directly on layer 1. So the transactions are not computed on layer 1, they're only saved as call data, which is a cheaper way of doing that and more scalable. But the transaction processing or the state transitions are done only by layer 2, unless someone detects fraud by layer 2 and challenges it on layer 1, which then arbitrates the dispute. So kind of like with Plasma, layer 2 is an arbitrator, or you can think of it as even a court, where in the optimistic cases, and this is where the name optimistic comes from, in the optimistic case, if the computation is done correctly and nobody challenges it, then nothing has to happen on layer 1. Everything runs smoothly. If an operator is malicious or somebody tries to commit fraud and claim that some state is valid when it's in fact not, then that can be proven in the court of layer 1 and resolved there. So optimistic rollup scalability is more limited. It's linear with layer 1 scaling because, again, you're relying on layer 1 to store all the transaction data in the state. So you can get on the order of 100 times layer 1 capacity, meaning 2,000 or 3,000 transactions per second, as the maximum theoretical throughput for all rollup chains combined, assuming all of layer 1 capacity is consumed by the rollup. So this is not really a good assumption. Let's say, for example, 50% of the layer 1 capacity can be consumed by rollups, then the total combined throughput of rollups would be reduced by half. So, and if you have multiple rollups in parallel, the capacity, well, the total capacity doesn't change. So the total capacity is limited by layer 1. All the rollups have to share that sort of layer 1 capacity. The advantages of rollups, optimistic rollups in particular, support general computation. So you can have an EVM compatible optimistic rollup chain that runs your Solidity smart contracts without any or minimal modification. And it's extremely secure and decentralized because rollups don't rely on an operator to store transaction data. Since all the data is stored on layer 1, we rely on layer 1 to store the transaction data. We don't rely on an operator. So if the operators become malicious or disappear, you can still continue doing transactions on the rollup chain. The disadvantages of optimistic rollups, one of the biggest one is sort of there's a long latency, similar to Plasma. There's a latency of hours or days to on-chain and cross-chain transactions. This is also called a withdrawal delay. So if you have funds on layer 2 in an optimistic rollup chain, and you want to withdraw them to layer 1, you have to wait for this challenge period, which could be could be days. And like with Plasma, there's a way to mitigate this for fungible assets. So if you have tokens like Ether or ERC20s, and you want to be able to withdraw them or transfer them quickly and easily between layer 1 and layer 2, you can have a liquidity pool provided by a liquidity provider that allows people to exchange on-chain versus off-chain tokens, but there is some capital costs associated with this. Key projects in the optimistic rollup space are Optimism, Arbitrum, and Fuel. ZK rollups are similar to optimistic rollups in that all transactions are written to layer 1 as call data, along with a state root. And ZK rollups also write a zero knowledge proof that the state was computed correctly. So the computation is done on layer 2, and the state is computed on layer 2, and then layer 2 generates a zero knowledge proof, which is submitted to layer 1 and verified by layer 1 before the data is accepted. So you can kind of guarantee that all of the data stored on layer 1, the transaction data and the resulting state, is valid and correct because it's been proven and then verified by layer 1. So you get kind of the same scalability, roughly on the order of 100x layer 1. So a few thousand transactions per second is the maximum theoretical throughput for all rollup chains combined, including optimistic rollups and ZK rollups. On the upside, there's no withdrawal delay. So once a transaction is finalized, you can withdraw your funds to layer 1, which can result in greater capital efficiency. They're also not vulnerable to certain economic attacks that are faced by fraud-proof-based systems in high-value applications. And they're extremely secure and decentralized because, like optimistic rollups, there's no reliance on an operator to store transaction data. On the downside, ZK rollups have limited support for general computation and smart contracts. This is something that's evolving rapidly, and now there are specialized languages available with most of the ZK rollup solutions to do sort of general computation, but you can't sort of take your existing smart contract in Solidity and port it to a ZK rollup. So they're not AVM compatible. They use a custom language for that. Generating the ZK proofs takes high computational power, so you need a pretty high-end and expensive server chugging away for several minutes to generate a proof, which means that if you have a low throughput, if you're only doing a few transactions per second, these may not be cost effective because the prover cost may outweigh the transaction cost. They have slower subjective finality time, which means the time to finalize a transaction on layer 2, typically 10 to 30 minutes to generate a ZK proof. So you may have to wait that long to sort of consider your transaction finalized on layer 2. But on the upside, once that's done, and once that proof is accepted by layer 1 and finalized on layer 1, then you've got full finality on layer 1 because there's no dispute time delay. So longer time to finalize on layer 2, faster time to finalize on layer 1 with respect to optimistic rollups. And then ZK rollups use sort of complicated new, it's been called moon math, ZK technology. The upside of that is that it's evolving rapidly and expected to improve significantly over the coming years. The downside is that it's evolving rapidly and it's new stuff. Key projects in the ZK space are Loopring, Starkware, Matter Labs, Aztec, and Hermes. And we have Validium, which, like ZK rollups, uses zero knowledge validity proofs in the same way. And the only difference really is that transaction data is stored off chain, off of layer 1 on a layer 2 network. So this gets you much higher scalability, like Plasma, which also stores data off chain. You can get probably on the order of tens of thousands of transactions per second per Validium chain. And you can run multiple of these in parallel. So you can add up the capacity to hundreds of thousands, maybe millions of transactions per second if you run them in parallel. Like ZK rollups, you have the advantage of no withdrawal delay. So no latency between the time you do a layer 2 transaction and the time you can do a layer 1 or a cross-chain transaction with that state. So you get greater capital efficiency. The downside of Validium, again, limited general computation support, high computational power to generate ZK proofs, same as ZK rollups, slower subjective finality time, faster full finality time, same with ZK rollups, and it's still complicated new kind of moon math technology, which is both good and bad. Key projects in this space are Starkware, which has Volition, Loopring, Matter Labs, ZK Porter. And then finally, we've got some hybrid. Okay, sorry about that. My headset died, so I'm going to continue with this mic. Hopefully you can hear me as well. And go back to sharing my screen. Here we go. So, and presentation mode. Sorry about that. Okay, so we have hybrid solutions which combine the best parts of multiple layer 2 technologies and may have configurable trade-offs. So we've got Arbitrum, which has a design called sidechains and state channels, which kind of combines benefits of both sidechains and state channels, as the name implies, but also can fall back to an optimistic rollup. So it's kind of 3-in-1. We've got Stellar Network, and we've got Starkware's, Volition, Matter Labs, ZK Porter. These are all different examples of hybrid technologies that can give you configurable trade-offs and the best of multiple worlds. So this is a lot to think about. This is a kind of complicated field. It's hard to get your head around all this stuff if you're just wanting to develop an application. So how do you select a layer 2 scaling solution? What do you need to think about? Well, some of the things are who's transacting with whom. So are you doing one-to-one transactions, one-to-many, many-to-many? What kind of transactions? Are you doing simple token transfers from one person to another? Are you doing token swaps like an exchange? Are you doing simple computation? Or do you need complex arbitrary computation with EVM compatibility and Solidity compatibility? What are your throughput requirements? How many transactions per second do you need on your layer 2? And what's your cost sensitivity? So is a 1 cent transaction okay? Or do you need to get down to 1,000th of a cent if you're doing micropayments? Who's going to pay the transaction fees and in what token? So is it okay to pay transaction fees in Ether or some ERC20, or do you need to pay in fiat? Do you need privacy? Do you need to keep your transaction details or data off of layer 1? So do you need a private layer 2 chain? How important is decentralization? Can you tolerate trusting an operator or validators to ensure that your data is available and ensure continued operation of the layer 2? And can you be the operator? So if the other operators go away, can you become an operator? That's one potential solution. How much value will be stored by the layer 2? So you're talking about thousands of dollars, millions of dollars, billions of dollars. That will affect your decision in technology. Liveness assumptions. So as I mentioned, some layer 2 solutions require you to sort of stay online and watch the network periodically, at least every couple of days, to make sure that your data is not, your funds are not stolen. So is this okay? Some applications, this may be perfectly reasonable, and some it may not. Latency sensitivity, do you need like really quick confirmations? How quickly do you need finality? How quickly do you need to be able to withdraw? So is it okay if users wait a couple of days to be able to withdraw their funds to layer 1? Or do you need instant withdrawal, or can you use a liquidity approval to provide that? Capital efficiency, so does the solution require capital lockup, and is that okay? And finally, time frame for implementing and deploying to production, because some of these layer 2s are more sort of mature than others. Some of them are still in the more experimental stages, whereas others are kind of ready for production. So one example of a decision process is the Reddit scaling bake-off that happened a couple of months ago. Reddit has this thing called
community points, which certain subreddits offer to their participants. And they want to make these community points available on Ethereum mainnet so that people can do interesting things with them, perhaps even involving them in DeFi in some ways. So they want to scale this up to support their 430 million user base. And they have certain requirements around scaling, decentralization, usability, interoperability, and security. They posted a challenge online, or an invitation for people to submit proposals to solve this challenge, and they received 22 submissions. And this is notable because these submissions were not just here's my solution, but they required a fair amount of effort to detail how the solution would solve the problem and to present a proof of concept. So this was an impressive result. Clearly, not everybody's going to be able to go through this process, but it's interesting to see how they did it. So now we're on to a panel discussion on layer 2 with Ben Jones from Optimism, Ed Felton from Off-Chain Labs, Alexander Vlasov from Matter Labs, and myself. So let me stop sharing my screen. Okay. Do we have the participants? No, we do not. Alex is here. Can we let Alex into the chat room? And Ed. And Ben, if he's here. Ben, are you here? Teresa, are you around?
I am. You said that you wanted
Ed Felton, Alexander Vlasov, and Ben Jones, if he's on.
Okay, 1 second, let me.
Hey, Alex.
Hey, Tas.
Hey, yo, can you hear me?
Yes.
Oh, my name is ASDF. Ah, that's funny. I'm Ben.
I figured it was you. All right, ASDF is Ben Jones from Optimism, and we've got Alex Vlasov from Matter Labs and Ed Felton from Off-Chain Labs, which is the creator of Arbitrum. So thanks for joining, guys. So my first question is, we've seen really rapid evolution of layer 2 over the last 3 or 4 years. So for example, rollups were basically unknown a year and a half ago, but now rollups are kind of all the rage. Do you expect to see more major breakthroughs over the next few years and totally new technologies? Or do you think that there will be mostly incremental improvements and maturing of the existing layer 2 technologies over the next couple of years?
I guess I'll jump in on that one. That's right. I think we're going to see. Breakthroughs. What we have today is a lot better than layer 1 in a bunch of respects. But when you look at the performance, it's that I think your slides with the trade-offs of the different approaches really kind of helped put into context what's going on here. There's a lot of space for breakthroughs, and I think we're going to have systems that offer more flexibility, that offer stronger security guarantees, and that can operate at full native code speed. That's where our roadmap leads us to be in the coming years. And there's a bunch of breakthroughs that will be needed, but I think those are pretty clearly in view.
I would say it greatly depends on what you call a breakthrough. Do you call, for example, EVM compatible transactions on ZK Rollups a breakthrough? If you expect it, then I would say yes, it would be definitely possible in the next year. I would hope for it. Else, I should put a correction here is that actually making zero knowledge proofs is not expensive in case of rollups. A zero knowledge proof per transaction is much cheaper than a single byte of data placed on Ethereum mainnet. Even if the gas prices are not insane, and even if Ethereum price is not as it is right now. So it's actually not expensive. It's much cheaper than the data you will put on chain, even 1 byte. So I cannot project for all areas because it depends a lot. Like maybe there will be another zero knowledge proof system more efficient. Would be great. We didn't have proof systems with universal trusted setups until early last year, and we've seen how much it evolved over 1 year and a half. So it just depends what you call the breakthrough. The usability will definitely improve.
Yeah, great. I mean, I guess I would consider that sort of improvements of existing technologies. But yeah, I mean, it's significant improvements. So
yeah, I mean, we already have 4 possible cross options between validity proofs and data on-chain or off-chain. So you will still have somewhere to choose between those 4 options. It's just their implementation will become better. And whether you call it a breakthrough in some small particular part is actually up to the final reader. But what I really would want to see as better solutions for data availability in general, one of those would be the Ethereum 2.0 itself, which is data availability engine largely.
yeah, good point. Good point.
Yeah.
Ben, what's your take?
Can you guys see me, by the way? Okay.
No, we don't.
Cool. I can't figure out how to put my video on, so I just look like some sort of ghostly ASDF in front of you all. Anyway, I think it's on my end, so maybe y'all need to do something, but not sure. I think I agree with.
Okay, we lost him.
Aha.
There you are.
You lost me, but for a greater cause, because I've appeared.
Okay.
Hey y'all. I think I agree with what both of the panelists said, and it really comes down to semantics of what is a major breakthrough. I think one of the cool things that you had in your slides, Tosh, was like that sort of 2x2 matrix of these different scaling solutions. I do think that over the past year, we've done like the forefront of categorization of L2s, like understanding what are the sort of building blocks that we have access to build these L2s. So I think in terms of identifying those building blocks, if that's all you're willing to count as a breakthrough, there's probably still more things in the pipeline, but in the short term, we have a lot of incremental improvements on those to go. In the longer run, who knows? I mean, I would be super excited to see, other crazy things that we can't even comprehend right now. Most of the things that I see in the pipeline, I would consider incremental improvements, albeit very important, awesome ones.
Fair enough. Yeah, some of those incremental improvements might add up to a breakthrough. Okay, next question is, there are so many different layer 2 technologies and even more layer 2 implementations, it's kind of enough to make your head spin, especially if you're new to this field. What do you think the landscape's going to look like in 5 years? Will there be even more fragmentation and even more sort of layer 2 projects to consider? Or will there be some sort of consolidation where most projects and applications consolidate around a couple or a small number of winning layer 2 implementations?
So I guess one question there, Tosh, are you asking about, when you say implementations, do you mean like deployed chains, or do you mean like the back ends supporting them? I think is one useful question.
Good question. I guess I mean code bases, but yeah, you could also think about it with respect to deployed implementations. So like if there are 3 deployments of the same code base, is that 3 implementations? Probably, yeah. I guess the question I'm asking is, do you see a lot of consolidation where the majority of DeFi apps, for example, are running on the same layer 2? Or do you see like hundreds of different layer 2 implementations or instances of those being deployed and kind of everything spread out across them?
Got it. Yeah, I mean, as far as our thinking around this, we often think about, I think, deployments more than tech, because it's all about like users and what people are actually doing. I think we predict that there's probably going to be like a power law distribution in the long run of layer 2s. So like it's depending on how you interpret that answer, that maybe means yes or no. It seems likely that what we see today is that being in the same sort of economic domain where people can transact within that domain is a sort of very slippery, frictionless thing that seems to be very useful for these money Legos. So it's our view that that'll probably continue, but there will definitely be a distribution of other implementations because there's tons of awesome work going on.
I think you're going to see a few families of solutions that that are sort of targeted at particular different categories of use cases. And I say families because of the usual issues that arise among things like versioning as products improve, right? That you're not going to see everyone on one single giant L2 chain. And I think you're not going to have 2 or 3 L2 chains. Just if you think about the economics of it and the practical issues around how the market tends to develop. But I think you'll see a consolidation in the basic technology stacks, and you'll see a few sort of technology families or product lines that get momentum. And over time, there'll be a conventional wisdom about, well, if you have these kinds of needs, go over here. If you have those kinds of needs, go over there.
Yeah, I think Ed just gave almost incomplete answer, but you also had it in part of your presentation when you started to mention network effects. Ethereum itself is great, especially due to its network effect and your ability to transact and interact with any other application. So eventually we would be seeing the consolidation, which would include versioning, potential merges of different rollups to some common address spaces, for example. But before this, I would say there will be many participants in the next few years. In 5, we potentially will see already a consolidation. But I wouldn't neglect some special instances for special purposes for applications like privacy, for example, for private trading, where in private layer 2 solutions, you intrinsically have a fragmentation, because as you kind of expose a small part of information in flight, when you have an interaction is like fact of interaction, maybe not the amounts or who was the sender and who recipient, you would see that one application interacted with another one. Whether you would want or not to disclose this information is up to users' preference. So I wouldn't neglect that there will be some special solutions focused on privacy.
Fair enough. Good answer. Okay, my next question is, what do you think are the main things that need to be built or the technical problems that need to be solved before we'll see the majority of Ethereum applications and transactions happening on layer 2?
I mean, I think it's pretty clear what the market seems to want. The market wants low cost. It wants EVM compatibility, complete EVM compatibility, not 98%, and it wants it as soon as possible. Those are the things we have to do, and that is our, those are the things we come back to every day in trying to build what we're building, right? Compatible, low cost, and ASAP. Everything else is in the noise by comparison.
Go ahead.
Yeah, I like that. I definitely agree with you on what the market wants said. I guess one framing of how we think about that is a lot of the tech is solved, but there's a lot of experience that I think still needs to be solved for. Both developer and user experience are like critical things, I think, that are stopping the adoption of crypto in general. And I think we have to solve those problems if we're going to make L2 successful. If I were to identify one of the big categories that isn't sort of just a plug and play system, it has to do with the existence of multiple chains, right? So in Ethereum development today, you only have one chain, right? It's called Ethereum. And in these various scaling solutions, right, we're adding layers of complexity, and these have these very good properties from what the market needs in terms of scaling, but it also adds overhead. How do developers build systems that have multiple chains? How do users understand what is going on when they're using those applications? So those aren't fundamental tech things at like the stack level of implementing the protocol, but I think they're critical to get people to make the move, even in a market where people are really dying for lower costs.
Yeah, usability, wallet support. What's your take, Alex?
Well, the support was mentioned, but I would say that even before there will be a mass migration to layer 2s, or like we still would see a specialized application, maybe just some large applications would move completely to layer 2. I would expect that one important part for end users would be some kind of user interaction transparency. So the user may not even kind of know if he doesn't care whether his funds are on layer 2 or layer 1. So if he would want, for example, take his money on layer 2 and make a smart contract call to some layer 1 contract or application, maybe store his funds somewhere temporarily and then go back, this would be an important part. So the transparency of going back and forth, both in like execution time, finalities, tools, the simple user interface, even this part is important. But I would expect that only a small set of these problems has to be solved kind of by layer 2 developers, just to give a technical ability to cross the boundary, and then just gives a tool for end users to be able to observe it as a kind of single address space. Yeah. Ed, please continue. Yeah.
Sorry. A bunch of these user experience issues are issues that exist already on Ethereum, or really any system like this. It's kind of awkward for users to get connected, have wallets, deal with the latencies that are inherent even in using L1 Ethereum, right? And people are working on those issues, of course, but and L2s can help. But fundamentally, it's about removing the speed bumps that prevent people from moving naturally across. My view is we don't have to invent a huge amount of new stuff for that to happen. I think the market will find those solutions if the L2s don't get in the way.
Yeah, fair enough. Okay, we've got a couple minutes left and there's a couple audience questions. So let's see. The first question, well, there are two, but they're kind of rolled into one. So do you see any benefits of layer 2 on private chains? And which layer 2 solution is better for providing privacy? Anybody want to take that?
I would love to take that one. Our Arbitrum SCSC, Arbitrum sidechains that you mentioned earlier, is a great solution for private consortium chains. It has the advantages of Rollup, but it does not require that the data be on chain. It's basically has the advantages of Rollup, except it's a permissioned product. What that means is your data does not need to be posted on main chain, and only the participants in your chain need to know what's on it. So privacy comes naturally in that kind of model. So yeah, that's something that L2s can very much support. Rollup style L2s don't do that because their security model relies on all data being available to everybody. But there are other approaches that do, and I think that's going to be a growth area.
Yeah, totally. And so the first part of the question was, do you see any benefit to layer 2 on private chains? I would think not. Private chains kind of have their own scalability solutions, and I don't really see why you need layer 2 on a private chain. Does anybody have a different thought about that?
I would even say that the data location is not that relevant on private chains. If you know also participants, you can the same way agree who stores the data for any layer 2 which you connect to it. So there's a difference between data on chain and what we usually call the rollups and data off chain, like for Plasma, Validium, or whatever. It's just disappears. So it's then you just start to talk about, like, for example, if you wanted privacy in Zcash styles and you would want to make a layer 2, which would do this just because you want their knowledge, but not just because you want some part of the data to be well parted, for example, or for any other reasons like scaling. But I would say if you want privacy, you could get a benefit. Like if you want to have perfect privacy, in the sense not just not everyone sees the data, but like literally no one knows what's happening. Only in this context of privacy, I would say.
Right. Good point.
I mean, so on that question, it kind of depends how large the group is that's doing if you're doing a private consortium chain. If there are like 3 entities together, adding another layer doesn't necessarily help you. But if it's a consortium of 100 and there are little groups of 10 that go off and do things together for a while, or there are interactions that involve only a subset, then you might benefit from actually doing some of that on a layer 2 on top of the private chain.
Right.
Layer 2 really excels when you have activities going on that a subset of parties really care about.
Excellent. So we're out of time for the first hour. We're going to take a 5-minute break and then get into the second hour. So please stick around, and we will come back with these 3 fine gentlemen to talk about each of their layer 2 projects in more detail.
Okay, we are back. I hope you can hear me because I got my headset back on. Please.
Yes, we can hear you.
Fantastic. All right, so this next hour I've called technical toe dipping into various layer 2 technologies. We don't really have time for a deep dive because layer 2 is a pretty complex field, but each of these three representatives from their projects will give us about approximately 10-minute overview of their layer 2 scaling solution, and then we'll have another sort of panel discussion with some Q&A. So Ben, would you like to go first? And oh, sorry, one question from the previous hour that we didn't get a chance to answer, this is an audience question, was who is doing the computation with rollups, ZK or optimistic, and what consensus algorithm are they using? And how can we be assured that collusion doesn't happen here? So maybe if you can touch on the answer to that during your talk, you probably would have otherwise, but just to be sure. So Ben, would you like to go first? And I will stop sharing my screen. Do you have slides?
I do indeed. I do indeed.
Go for it.
My screen sharing is disabled though, so we got to enable that.
Oh dear. Okay. Can we fix that?
All right, that worked.
There was a question, will the webinar be recorded and shared? Yes, I believe it will be recorded and shared.
All right, we're gonna fingers crossed nothing embarrassing pops up when I hit this random button that I can't see. Aha. Oh, okay. Just need to do that. Oh, looks like I've got to rejoin to be able to share my screen. So I'll do that.
Okay.
All right, we're back.
You're back.
Oh, I'm back with my ASDF name as well.
That's okay.
Oh, looks like y'all. Oh, great. Here we are. Wonderful. Okay.
There we go.
Cool. Hello, everyone. Let me hit present. Can y'all still see that?
Yep.
Looks like it. Cool. Let me see if I can click. I can. Hey guys. So I'm Ben. I'm one of the co-founders of a team working on some of these lovely scaling solutions called Optimism. And we're building something called Optimistic Ethereum. And I will talk about that just a little bit today. Really what I want to do, whenever I'm on something that is live and interactive, what I really want to do is do live interaction things. So I'm going to honestly breeze through some info that you can totally find on the internet about us if you want. Then I'll talk a little bit about like sort of our philosophy and how maybe some things that wouldn't be as obvious if you go to optimism.io. And then I'll honestly open it up for questions. So I'm hoping that y'all can come up with some great questions to dive into for the remainder of the time. But if not, I've got some other backup slides. Cool. So what is Optimistic Ethereum? Optimistic Ethereum is the optimistic rollup chain that myself and my team are building. What is it? It is an optimistic rollup. So it's an L2 that Tas talked about at the beginning. It has the lovely properties of the EVM that you know and love, but you can put it on L2. So what does that mean? Of course, that means we get some, L1 censorship resistance and security. So that's very exciting. Another thing that Optimistic Ethereum provides that's not necessarily the case in all optimistic rollups, so maybe it's notable, is we have a very awesome role that allows us to have instant UX. So I was talking before about the problems of getting users using a system in a manner that seems like the rest of the internet that they interact with, not like a regression. And so we have some really cool tools that allow us to give you super fast, low latency confirmations on your cheap transactions. Again, I could dive into all day long how amazing money Legos are and like the ability and the awesomeness of being able to shove these different components together in a composable chain. But I think really what I would do is just say, go try it out for yourself. So if you go to that layer2.minter.synthetics.io, you can go and try our testnet, which is just on the tail end. So maybe go try quickly before it runs out of time. But it's very exciting. We're super pumped that some of the most complex EVM contracts that are running in prod on layer 1 today are ported to layer 2 and running smoothly. So it's pretty dope. So please ask questions about the protocol, but since Tosh gave an overview, I didn't want to dive into a bunch of things that was going to get repetitive. So instead, what I thought I would talk about a little bit is just the philosophy that optimism goes about as we are building this solution. And there's sort of three tenets there. The first one is pragmatism. So we work very, very, very hard on an issue that is one today, and it is a big one, right? A couple of years ago, we weren't in the position where the Ethereum network was getting congested and gas prices were going through the roof. We are now in that world. So everything that we do is guided by getting this solution to Ethereum that can help them scale in a production environment today, because it is a problem today. One of the results of that is that we work really hard not to reinvent the wheel and just build things that are modifications to the incredible open source Ethereum that already exists. So if we're talking to a panelist of Enterprise Ethereum Alliance people, I feel like I'm in very good company with that, because I'm sure that you guys are able to utilize awesome things that happen to Ethereum for layer 1 for your private and consortium chains like we were talking about. And of course, using layer 1 itself. So we can see here, we've got the EVM that we're running, and we even have, I think, what is an unofficial logo for Go Ethereum for guess, right? And what you can see down here in the middle is a diff, right? We got some red lines and green lines. And I made it really small to emphasize that we have a small diff, right? It's all about building small modifications to existing systems to get them to run on L2. So we're really excited about being able to do that in a way that can jump and stand on the shoulders of the incredible giant that is the Ethereum layer 1 itself. Another big point of our philosophy is developing out in the open and being collaborative. So everything that we do as we do it is around on our GitHub for you to investigate and dive in and explore and learn about. And the other thing that we're really excited about on this collaborative open source front, and also something that comes out of the result of having this small diff, we're very, very excited to have a very symbiotic relationship with Ethereum, and especially Ethereum 1.x, new Ethereum development. So I have on the right here a diagram that I pulled from some ETH 1.x research on a state try for stateless Ethereum. And one of the coolest things that we can do is a lot of the tech that goes into building new Ethereum research can be deployed on layer 2, and even probably sooner than on layer 1, because you don't have to fork it in. So that's very exciting, and being able to collaborate with people in the existing Ethereum research community on how to make a layer 2 version of Ethereum that's even more dope and awesome is super great. And the last philosophy that we take is iteration. We've got to learn from the community and do things for the community. So we've been very lucky to run 2 public testnets with Synthetics, who has been an incredible partner. We've been very fortunate to be able to not just build in a vacuum, but be able to test in an environment that has real users and real people angry on Discord when things break and excited when things go well. So being able to learn by having something out in the wild that users are learning is something that we think is absolutely critical. And we've just found huge dividends getting paid out as a result. So that's all I did for these slides, because I really am hoping y'all have some dope questions to answer. But if you don't, and maybe I'll let Tosh take the reins and see if there are any. So please ask away. If not, I can go over some more slides and talk about one of our most frequently asked questions. But I think we should pause here and do some questions.
That's great. Actually, I'd like to hold questions until after everybody's gone through their 10-minute talk, and then we'll have hopefully the rest of the hours for questions.
Cool.
So, yeah, thanks, Ben. And Ed, would you like to go next?
Sure, let me go. Screen sharing. And okay, great. Yeah, so I want to talk about Arbitrum. I want to talk about Rollup, which is our current product, and Sidechains, which is the more enterprise-focused product that will come next. So our current product, Arbitrum Rollup. One of the things we're excited about here is our public testnet. It's been up for about 2 months, really open to the public. A lot of people have come in and used it. We don't know who they all are. We don't know why they've done some of the crazy things they've done. That's what happens when you open something up to the public. You learn a lot that way. So you can go to arbitrum.io and use it right now. One of the things that really differentiates our solution is the level of compatibility with Ethereum. So right here, I have the instructions for porting your application to Arbitrum. You don't need to use any special tooling. You don't need to recompile or use a special compiler. You don't even need to download any software. Arbitrum nodes offer exactly the same exactly the same API as Ethereum nodes. So you just point your RPC provider at an Arbitrum node like the one here, shown here, and then you're good to go. You can deploy your contracts. You can send transactions. This is bit for bit compatible. To deploy a contract, you send literally the same bits you would send to Ethereum. To send in a transaction, you submit exactly the same bits you would submit to Ethereum via the same API. So it really is that easy. And that's been a big focus. If you want to see what's happening in our testnet, you could look at the Block Explorer, which shows the L2 transactions that are happening. Here's a screenshot from about a couple hours ago. You can drill in on individual transactions. Here you see this transaction. And the thing to note is in the middle, layer 1 gas used 1931 gas for this particular transaction, which I didn't cherry pick. This is just the transaction that happened to be at the top of the Explorer when I happened to take the screenshot. So it's all there. You can really see what's going on and try it out. So we're really excited about that. And we've learned a huge amount. And it's really helped us get a lot closer to being ready to launch. So I'm going to talk a little bit about the sort of philosophy of how we build the system. Of course, we're pragmatic. Of course, we're open source and all of those things. I want to talk a little bit about how we develop things the way that we do, and how we what we do to get the layer of the kind of flexibility and the kind of compatibility that we do. And the key question here is which functions get done where. You can do things on legacy computers that is cheap and fast, but they can't necessarily be trusted because every one of them belongs to some party who has an interest. You can do stuff at layer 1, stuff in your protocol at layer 1 and so on, that's trustless, but it's relatively expensive. Layer 2 is really where the sweet spot. It's trustless and it's also cheap. So the name of the game to build a system that's going to work is and really solve people's problems is to put as much as you can at layer 2. And so we move a lot of things that are in layer 1 or on legacy computers and other systems up to layer 2. And that gives us both trustlessness and speed, and most importantly, flexibility. That's how we're able to get the level of compatibility with Ethereum 1. And it's the way that we're able to have more headroom for move our products forward. You want to see an example of an application on the system? Here is one. We took Uniswap version 2. We ported it over. The contracts port pretty straightforwardly. We added some things to the UI, so it's evident that you're using a layer 2. You can go and try this right now at the URL that's here. So it's an example of the sort of how easy it is to port. Okay, so now let me switch gears from talking about Rollup to talking about side chains. Our current product is Arbitrum Rollup. Future product that we're developing that is about maybe 6 months behind Arbitrum Rollup is what we call Arbitrum side chains. And here's the difference. If you compare Arbitrum Rollup, or really any Rollup, against an Arbitrum sidechain, the main difference is that it's a move from the validators, that is the parties who actually execute your transactions and who participate in the correctness of the protocol. And in response to the question that was asked earlier, on Rollup, anyone can be a validator, and our algorithm, which we've published in a peer-reviewed publication, guarantees that any one honest validator can force correctness. So it's permissionless. You yourself can force correctness, or you can hire someone to do that for you. So that's Arbitrum Rollup. Along with that, or in order to make that work, the transaction data is stored on-chain, like in other rollups. Of course, the computation and storage are off-chain. So when moving from Rollup to Arbitrum sidechain, the change that we make is we make validation of a chain be permissioned. So there's a permissioned set of validators, and that means that you can talk about things like what all the validators agree on. So we still provide the very strong guarantee that any one honest validator can force correctness. But this allows us to move transaction data off-chain and allows us to gain additional order of magnitude decrease in cost over what you can get with something that needs to put transaction data on-chain. The other thing that this gives you is the ability to have a chain that's private if you want. You can always publish what's on your chain, but you can keep it private. You can hold it under encryption on the chain. And of course, the security of both is fully rooted in Ethereum. What you need is for Ethereum to operate securely and for at least one honest validator to be present. So we think the Arbitrum sidechains product is really an excellent match for enterprise and especially private consortium type chains, as we discussed earlier. Okay, so in terms of roadmap, our first fully functional public rollup testnet rolled out in October. We'll have a rollup release candidate this month, which will enter security audit by the end of the month. Once the security audit is done and we deal with any issues that are discovered there, will be good to launch on mainnet. The side chains product, which will sit alongside the rollup product, we expect to have a release candidate in Q2 of 2021. And there's a lot more on our roadmap, a lot of improvements to efficiency, functionality, and security that are further down the road. And that's all. I'll pass the baton on to Alex.
Awesome, thanks, Alex. Go ahead.
Because as a part of the preamble for this call was like, I have to talk about both Rollups and Validium. I didn't make a slide, so I will try to make my talk a little bit more like educational part.
Sure.
So if Tashi sees that we run out of time or just you want to spend more questions, just tell me. It's more like for general education, so of people in general. As I represent Metal Labs, so the Metal Labs as a company has developed the ZK Sync with the first version released in June of 2020 of this year. Which is a ZK rollup where validity of the state transition is proved using zero knowledge proofs, and the data is posted on chain. And first of all, since I say this phrase, why the data is posted on chain is only for worst case scenario only. So if everything goes well, if everyone is honest, validity of the chain is proven. So that's fine. But let's say you want to move your funds from layer 2 to layer 1, and the operator who would be responsible to process your request is just refusing to do it for you. We don't talk here about whether there is a single operator for a ZK rollup, because it's not that important. The validity of the chain is still only reliant on zero knowledge proofs and also the honesty of this entity. But this entity still can censor you. So for this, like exactly worst case scenario, you should have a tool. And for this tool, if you go all the way into the escalation chain, will result as that the layer 2 chain should halt, and everyone should be able to just pull out their funds. So their funds are just as safe as they were on layer 1, whereas the data is always available due to consensus. So it's only worst case scenario, which basically affects zero knowledge based applications, whether it's rollup or what was called here Validium. Like this term I think was made by Starkware, who is not as it's called. But the main difference is only whether we store the data on layer 1, the smallest possible amount of transaction data, which allows everyone to know what is their state in layer 2. By state, I mean arbitrary state, but let's say how much funds each of the users have. So for Validium, this data is still kind of provided by external third party, which you cannot enforce to disclose your data. So it's still kind of viewed as another layer, but only responsible for data availability. So whether it's layer 1 in one case or just some consortium in another case, someone stores your data, and in the worst case, you can either read it permissionless from layer 1, just looking at the chain, or you have to request it from some party, which can always say, no, I will not give you data, and this opens some exploits on you. So, but the essence is the same in both cases. We use zero knowledge proofs, which allows us to use old untrusted computers as trusted computers. Of course, we get some overhead, but this overhead is negligible compared to kind of cost of the consensus in Ethereum layer 1, as I told. Actual cost to rent a server, like you rent it from, let's say, Amazon. You start a proven routine, which takes 5 to 30 minutes to complete, with a lot of room for improvements. You end it and you just kill the server. You paid for only 30 minutes of time, and only when you need it to make a proof. And when you calculate it all by the end of the day, you get that your cost to prove one single transaction is, even if this transaction is actually much more complicated than what we have right now. So if we talk about smart contracts even, then you pay less than you would pay for one single byte of data sent to Ethereum if this byte is non-zero. So it's not that expensive. So we moved to zero knowledge technologies now, which should also clarify. First of all, they were perceived more like in privacy area due to the historical reasons, the development of the seed cache, which use zero knowledge proofs to create shielded transactions. And they use the power of zero knowledge proofs in a side which can be described like, I can prove you that this function on this input gives this output, but I will not tell you exact values of all intermediate variables which this function used, but I can prove you that all assignments were correct. So if you look at this more, a little bit more globally, you can say that you can apply it, for example, to your balance in some chain. So you can say, well, this balance is not transparent. Let's say it's a hash of the balance actually with some salt. But I know what's under this hash. I deducted my transaction amount properly from this like shielded amount. I didn't encounter any underflows, so I didn't produce money out of thin air. And this is a part which I sent to another party. For example, this would be a good example of zero knowledge proof, which is in application of privacy. And this is what roughly Zcash was about. But then we moved this definition of ability to prove arbitrary function to a little bit higher level, which was a global state transition from one state to another, whereas under the state, we mean the full set of user balances in our system. And later on, we will be able to mean something like state of users, smart contracts, their storages, maybe some potential acts of interaction. And then we can prove that we had a block which taken old state, applied all transactions in sequence to this state and made a new state, and that all those transactions were correct. So we see a valid signature for every spent transaction. For every transaction, we didn't encounter underflows or overflows, for example, that senders and recipients were correct, and et cetera, et cetera. So we just taken this definition of zero knowledge proof to the next layer. And this was kind of the historical perspective. And just to finish it, I should mention that even while the history of proof systems for zero knowledge proofs is, I would count it 7 years old from 2013 publication of Pinocchio proof system, which was actually one used by Zcash when they made the first version. I like personally, it's only my personal opinion. I count it as like a birthday for zero knowledge proofs as we know them today. There was a huge road of development. For example, in the early days, you had to do the ceremony, which was called the trusted setup, which you had to do every time you launch something based on zero knowledge proofs. And early last year, we were able to remove this part, and later on even kind of remove the largest burden of this part. And later even, and by the word Starkware also just remove the ceremony completely and make also proof systems probably quantum secure. So there was a huge number of achievements during the last 7 years, and I would say we will see a lot of unexpected breakthroughs. Here, I would say word breakthrough, because even while for layer 2 landscape, it's minor improvement that your user will never see or appreciate. I would say no one would appreciate what's the change of complexity under the solution. But for cryptography and zero knowledge part, we will see the breakthroughs, which will allow us to use zero knowledge proofs more efficient, make proofs faster, like maybe kind of pay even less, for example, to make a single proof, reduce latencies everywhere, so it will not be 10 to 30 minutes for block finality. Maybe it will be just 2. And I would expect that I would see the breakthroughs in this field. Here, because it's already becoming quite technical, I would stop. And if there is some time left, I would just let's turn it to the questions part.
Awesome, thank you. Would you like to say something quickly about the general computation support on ZK rollups?
Like, I'm going back into history once again. So back in 2013, when the Pinocchio was presented, there was how it was presented. It was presented on proving an execution of a machine which was called the tiny RAM. And the code which it was executing was actually just a subset of C. So eventually, it's just more or less a matter of engineering work and complexity. Eventually, we will see an ability to run more or less arbitrary code. Then we can also have like another layer of technical, like pure technicalities. For example, as you know, Ethereum operates on unsigned integers, which are 256-bit long, which are not kind of machine native, which incurs overhead even on traditional machines and can kind of potentially incur overhead on executing EVM compatible code using zero knowledge proofs. But it will eventually boil down only to how much processing power you want to spend to generate one proof. So there is no fundamental problem why you cannot run arbitrary code. Even the code which you run in Ethereum, you cannot call it arbitrary, because you know that your program will stop eventually, or transaction will be rejected because you ran out of gas. And this is the only single part which actually differentiate between zero knowledge circuits, which have a bounded, let's say, capacity. So your program have to run for n steps and then either produce a result or just not produce a result. So this is kind of the same reflection as in Ethereum we have a notion of gas, which means that you cannot have a program which runs infinitely long. Thus, this way, I would also say that then the difference between EVM compatibility and running general computations will also disappear if we talk about the Ethereum in full with the notion of gas itself. If you would want to run a program which like infinite cycle, then no, you cannot do it.
Very cool. Okay, thanks everyone. So I've got a couple questions, and then let's see if there are any audience questions. If you have a question, please hit the Q&A button and or post it in the chat, and we'll try to answer it. So my first question is for each of you: what kind of applications do you think your solution is best suited to? Who would like to go first? Ben, maybe?
Happy to. The question is, what kind of apps are we best suited for?
Yeah, so what kind of applications are optimistic rollups best suited to, and maybe what kinds of applications are they not well suited to as well? Mm-hmm.
So, that's a good way to frame it. So I would say applications that are basically about sending a bunch of money around with no real logic other than a person's desire to make a payment, then optimistic rollup isn't a very strong fit in comparison to some of the others that you said, because the way in which optimistic rollup scales with this on-chain availability step does lower the overall throughput that you can get, and it increases cost. The reason that it's worthwhile is because smart contracts are what you get as a result. And as far as what we're focusing on the sort of money Lego world of smart contracts, where you want one shared composable environment in which many applications can be deployed and interact, and new applications can appear and also do that. So that's a pretty generic strength of smart contracts in general, and that's certainly something that we're extremely focused on, making sure that those people get a really good experience. Other than that, we also have some low latency work. So especially applications that have users making many frequent interactions, you get a lot of benefit from UX because of that.
Oh, Ed, you're on mute.
Yeah, thank you. Yeah, so I guess I would start with an answer pretty close to Ben's for our rollup product. If you want instant finality, of course we offer that. And of course you can run general computation. The advantage of optimistic rollup is for applications that require more than a trivial amount of computation, because we don't have because the cost of computation is low relative to other solutions. And in the case of our solutions specifically, we don't have the same low gas limit that Ethereum has per block or per transaction. With respect to the sidechains product, as I said before, that's really well suited for private consortium chain kind of applications, or applications where you want to be able to build off the security of Ethereum, but you really care about having privacy for what's happening in your chain.
Awesome. And Alex, what about ZK rollups and ZK solutions in general? What are they best suited to, and maybe what are they not well suited to?
Yeah, so first of all, I should answer for part which kind of universally applicable without notion of like potential improvements in future. So if a solution requires like completely no liveness assumption, like something happens on the chain and no one should watch whether it happens at all or what happens in general, then you want like validity proofs instead of fraud proofs to rely on for security. Same way, if you want a fast finality for any reason, for example, let's say you want to move non-fungible assets through the border between layer 1 and layer 2 and you want to do it quickly. This is kind of universal benefits. For data allocation, I already answered in my previous answers. So if you want to consider worst case scenario that data can become unavailable at some point, which is most likely not the case for permissioned networks and consortiums, then you want to put the data on chain. If not, then any storage by some trusted parties would be fine. And for what's best suited and what's not, I can only answer with the notion of time. So, and this notion of time is only just amount of time which required to develop this tooling which would allow it. So right now they're best suited for types of transactions which have quite simple logic. So it's transfers, it's swaps, it's some form of EMMs, which are trading solutions. Maybe something else, and also for private transactions if you want to implement them, which is a separate question. If we look like half a year, I would say like year in the futures, then you can definitely count on Arbitrary to execute much more complex transactions, which would involve smart contracts as we know them today.
Cool. Yeah, it's impressive to see how fast CK technology is evolving. It's kind of mind-boggling. Great. So my next question is about interoperability. So we've got all these different layer 2 technologies, and we're going to have even more, instances of these layer 2s deployed. We don't want them to be isolated silos. So how do you envision your solution interoperating with other layer 2 implementations so that they're not all kind of isolated silos? How are they going to be able to interact, and how are you going to be able to transact between one layer 2 and another? Anybody who wants to go first?
Sure. Yeah, I think you could break that question into two pieces. One piece is about how to transfer fungible assets between chains, and the other is about other kinds of cross-chain calls and so on. Fungible asset transfer, I think, is a problem that's going to get solved. There are cross-chain atomic swap protocols. There are markets. There are new kinds of mechanisms. There's a sector of companies who are developing services to provide seamless transfer of assets across chains. And so I think that's a problem that will be solved. The question of how to interact in terms of a contract on one chain calling a contract on another one, that's something that is going to take a little bit longer to develop. It's not a fundamentally difficult problem, except for the issues around delays. All the solutions, all three of the solutions that you're hearing about here have some kind of a delay, either a delay for withdrawal or a delay to produce a proof or something like that, which makes synchronous calls between different chains a more difficult problem. Asynchronous interaction is something that I think we all are going to solve. I know we will have that in our product, the ability to make asynchronous calls, to make synchronous calls in and asynchronous calls out to general contracts on L1, which would enable us to do cross-chain calls in an asynchronous way. But I think general cross-chain calls are, for the foreseeable future, going to have to be asynchronous across chains that use different technologies.
It's a difficult problem. Anybody else?
Yeah, it's like for synchronous parts, you already also had it in the slides, you need a common notion of time, which is a layer 1. So without an explicit call to the layer 1, it's unlikely that we will see a solution in the nearby future, because if you would see some solution like this, you will kind of immediately see a possibility to interact between various chains in general, as soon as you have some canonical notion and reflection of one chain in another one. So you would be able to go, for example, from Ethereum to a side chain, not just to layer one, but to the side chain, because the problems are very similar in this essence. So without interaction with layer one, I wouldn't see it soon. Later on, if we will see that large layer two solutions will merge, then this problem will be kind of solved naturally, like merging the specs and kind of common transaction formats. With tools better and better developed, it will be much less a burden to update a layer two solution, even ZK-based one, to have some common format. And we will already find by this time efficient formats. So everyone will still want to use them because they're just efficient.
Interesting. So, Ben, any thoughts on this interoperability between layer twos?
Yeah, it's a very important and deep question. I think Ed hit some really good answers that are applicable to the both of us, because we have similar underlying mechanisms. I would say the one thing that I will emphasize is what it means to do asynchronous cross-chain communication, right? Means that you can basically send a message out, but you don't have a guarantee immediately of what happens as a result, and you definitely don't get a response back right away. And in that context, really what's missing is primarily developer tooling. There's a fundamental nugget of building block that we understand how to make cross-chain communications happen, but enabling developers to use those cross-chain communications in a meaningful way is the tricky part.
Anybody want to speculate on how long that's going to take?
So I think actually there's some lessons we can learn from web programming, right? Web programming, you have clients that are interacting with remote servers, and there's this notion of making an asynchronous request to somewhere else, and the answer will come back at some point later, and that triggers some kind of a callback. I think you end up in a model that is not so different from that. So we have familiar models that developers have worked with a lot. The timescales are different. It's not like pinging some server across the net where it's a fraction of a second until the result comes back. It's going to be longer than that. But I think in terms of what are the basic programming affordances, what's the basic programming model, I think people will learn from basically network programming. Just network programming at a sort of on a different time scale where you're talking about seconds or minutes of latency to get something from one point to another.
Yeah, I mean, that's going to be interesting on the UX side because users may not be used to waiting for minutes to see something happen.
Yeah. The other analogy I'd point to is the way that users interact with Ethereum right now. Like right now, you submit a transaction and it goes in the mempool, and then sometime later, maybe if you're lucky in a few seconds, if you're not lucky in a minute or two, it actually happens.
Yeah.
So that's an inherently asynchronous model. Contract to contract calls on Ethereum are synchronous, but interaction with users are inherently asynchronous. And so asynchrony is something that's all around us in these applications. And I just think, we work out how to use the programming affordances that people already know in order to figure out what structures to build here. I don't think we need to invent new computer science to do it.
Cool. We've got an audience question that is actually from the last hour, but I think this is a good time to address it. So the question is, for rollups, ZK or optimistic rollups, who is doing the computation? What consensus algorithm are they using? And how can we be assured that collusion will not happen within the rollup, among the rollup operators? Anybody want to take that?
Sure, I'll go. And I think this answer, well, may be similar. So for optimistic rollups, the basic scheme is that because the transaction data is one, anyone can check, anyone can do the computation, can compute along and participate fully in in the challenge or dispute protocol in order to ensure correctness. So anyone can. That's the first thing to say. The question is who will, and that basically is a question about economics and how chains arrange to hire or incent people to do validation. The other important thing I would say is that, and I think all of these systems, rather than using a consensus protocol, where consensus has this idea of kind of like voting, that if enough people say a thing should happen, it will happen. These are all using what I would call a correctness protocol, meaning that if there is a disagreement, that the system will determine who is actually right on the merits, so that one honest party can force correctness, even if everyone else is against them. So I think that's really important, and I think it's true of all of these systems, basically, that as long as someone honest is paying attention, the bad thing can't happen. So actually, just if I could add one more thing to bring it back to user experience, right? So if you're a user of this system, it's a lot like Ethereum. You can run a full node if you want, and then you're checking everything out yourself. You're fully participating and you know if anything is wrong, or you can choose not to and basically rely on there being a community of people who are doing that. And the same is true with with these rollups. You can run a full node and actually validate everything yourself and issue a challenge if something is wrong, or you can choose not to as a user and just rely on there being a large enough community of people incented by rewards to be doing that.
Yeah, with rollups and data on chain, like the reason for data being on chain is that for end user to have an ability to kind of synchronize your Ethereum node to the latest state. So if you want, you can actually start producing the blocks from this new state. But still, regarding the consensus, it's not that important for zero knowledge solutions. You can have a party, even like an outsourced party, who will make proofs for blocks. You only need to point this party to what is the content of this block. And so somehow we need to also determine what this is content. And for this, you would still want to run some kind of consensus just to kind of agree what is the content of this block. Whether it will be with slashing or without slashing or just a simple VFT, whatever it will be, it's more or less required for censorship resistance. So, because if there is only one or just three operators, they can easily collude and kind of censor your transactions if they want. And if they seem beneficial, they can try to run bots which will produce minor extracted values or something like this, which everyone would want to avoid eventually, which is less a problem for permission chains, but for public ones, still want to think about censorship. And even while for user, it's not end of the world, you still can trigger moving your funds from layer 2 to layer 1 if you completely disagree with the policy of entities who decide the content of this block. So you're still secure, but you will still have a negative user experience. You, at the end of the day, like we, like Metal Labs, we would want to avoid this part at the first place. So for this, we would want to see that entities who would want to determine the content of this block, of course, this content has to be valid, otherwise the proof will never come for it. And this is definitely a slashing conditions of some form. So we would want these entities to be decentralized and permissionless. So at least for this, there should be something which can be called a consensus.
Great. I don't have any other audience questions yet. If anybody has a question, please post it in the chat or the Q&A. Otherwise, do any of you guys have any questions for the other panelists or other things that you think we should talk about?
I would ask a few questions about technical details, but it's just not the right place. But I would want to chat with you guys in general later on.
Yeah, there could be some deep rabbit holes there.
Yeah, I guess I would just, I would just like urge people to go out there and try L2 solutions. L2 is not something that's far in the future, right? You could use our testnet, upload whatever contract you want. You could look for other testnets and see if you can upload contracts to those. And really, this is a thing that is on us. It's not something which is far in the future. And the need for it is obvious given the increasing cost. So jump in and give it a try.
Yeah, definitely. I mean, layer one's already congested. Now is the time to be figuring this thing out. How you're gonna use the layer one and layer two in your solution. We've got a question from an audience member. Which of these layer two solutions would best fit for plain vanilla payments at massive scale? Anybody want to take that?
Yeah, it was kind of a part of the previous question for which type of solutions, which type of transactions different solutions are best. So like you can definitely use zero knowledge based ones for just payments. For example, you can just go to the zksync.io and open a wallet like Mainnet wallet live solution, try it on a mainnet, see what's the user experience. At the end of the day, cost of transfer on any of the solutions with data on chain will be only determined by the data on chain. So for this, the end cost per user most likely will be the same. Security guarantees, it was described here many times, so let's not repeat, but it's definitely worth to go try, and any of those should fit the needs, just depending what extra parts you want. But for payments, all of those will work.
I think it also depends on who's paying whom. So if you are talking about if you have a network of say thousands or millions of people and anybody could be paying anybody at any time, that's going to be a different solution from, let's say you have a web service API and you want to charge a stable base of customers for each API call. So the Graph, for example, is an example of that. The Graph is a project that provides data queries and data on Ethereum. And they're setting up state channels so that they can charge per API call for their queries. And so each transaction will have a very, very small cost because it's using state channels. That's an example of a sort of one to few payment situation, which may require a different type of solution than something like where you have millions of people that could be paying anybody within the network.
Yeah, there are optimistic rollup type solutions that specialize in or really focus on more simple transfer type of applications that would also be worth looking at. Something like Fuel Labs would be another interesting thing to look at for those particular types of applications.
Mm-hmm. Yeah, Fuel is a rollup that is doesn't do general computation, but it's more scalable if you're doing just something simple like payments. We have another question from the audience. What do I, as a smart contract developer, need to do in order to make use of layer 2? Do I need to code differently?
Not if we're all doing our jobs right. More seriously, sorry, Ed. More seriously, the one thing you need to do is figure out how to get assets in and out of layer 2. So you need to code differently if you have users that want to talk to like a different layer 1 app, then you've got different requirements. If you just need them to be able to deposit and withdrawal, then you need to add that. So there's additional code that you need to write, but the existing stuff you do shouldn't have to be done differently.
Yeah, basically smart contracts, EVM smart contracts ought to run as written. This is something that I think the market demands, that that we and others are really focusing on, is to be able to support unmodified EVM code. We've built something that supports the same API, send literally the same bits you would send to Ethereum, and it will work. And that I think is the goal. So it doesn't need to be a big speed bump to get to try out your smart contracts on an L2. If, as Ben said, if we're doing our jobs right, then it should be very easy, and you can try it.
Yeah, for ZK Rollups now exist a set of languages which are able to provide user experience with like a standard programming language. You don't need about the underlying primitives for zero knowledge proofs. So like Think language, which we developed, is one of them. There is also a recent Cairo by Starkware, for example. And those are done I think this way, not to be as close to Solidity as possible, mainly for reasons that the Solidity is not the best language in the world, actually. And as we've seen many times, people did mistake with it. And even some parts of EVM in layer 2 start to kind of lose sense, especially in the key environment. For example, notion of CAS is completely not necessary. So for example, in Solidity, you would have to completely remove it, not to confuse the user. Like you have to inform a user somehow. I wouldn't be too much surprised if someone just makes a tool which allows you to just take a VM contract and also compile it to zero knowledge circuit, because at the end of the day, it's actually not that complicated or heavy. So I wouldn't be surprised that at some point it will be possible to compile Solidity just as it is, even while some parts of it are like do not make too much sense for zero knowledge environments, but you still would be able to run it. But for now, I would encourage to start with like if you want to like write a special application within area of finance, and you want security guarantees from layer 2, then most likely your choices is zero knowledge environment, and then special language actually makes sense. Yeah, like there are many parts of Solidity which are questionable and which I personally don't like, but it's kind of a legacy code at the moment.
Yeah, awesome. And I would just add that there are other layer 2s which do kind of require a different paradigm. For example, if you want to use state channels or something like Plasma, that's going to be a different way of thinking about developing your application. You can't just take an existing smart contract and port it onto state channels. Yeah, good answers. Thank you. Looks like that's all the questions, and we're running on low on time. So thanks everyone. It's been a good session. I believe the video will be posted online soon. I'm going to share my screen with my email address just in case anybody wants to contact us, contact me, and I can put you in touch with anybody else. It's tas@dienes.org. And for Enterprise Ethereum Alliance, if you're interested in membership, please contact jack.leahy@ent-alliance.org. EE is a great organization and helps educate and make connections with people about things like this. So thanks, everyone.
Thanks, guys.
Yeah, it was a great discussion.
Yeah. All right. Have a good day.
Thank you, everyone. This concludes today's EEA Education Webinar Series.
See you guys.